Okay, so welcome to today's lecture on neural networks and deep learning. Last week we did like an overview a bit on like what are possible like architectures, and maybe that was a bit abstract, but from today on now we'll try to dive deeper into to better like understand what each of these components mean in order like to have examples of exactly this type of architectures. And with this one, we will start today. We'll look into two major like architectures, which are commonly used in a lot of neural networks, that are on the one hand the time-delayed neural networks or convolutional neural networks, and on the other hand the recurrent neural networks. We look how they two relate to each other, how that like can be understood in the relation to last time. These are all like both are like networks which do this one-to-one mapping, so which like take a variable size input and transform it to another variable size input. And yeah, they are looking into the details, how it's implemented, and then especially for the RNN also go a bit further. So we first look into the basic RNN, and then at the end look to a specific implementation. So the overall idea stays the same, but for LSTMs, we'll see that they have a bit of a different way of how to calculate the new hidden state, which enables it to like perform better. And LSTMs are like one of the networks which are currently still are used if you want to use a recurrent neural net. To get a bit of a like step back, what we had looked at the beginning was, and what we mainly looked at into was this multi-layer perceptron, the standard feed-forward neural network, and this will be important because this is like always the basic structure that we apply some type of linear transformation on the input, like a matrix multiplication. How we've seen it, how that is then implemented in GPUs. Then we are doing some type of activation function afterwards, a nonlinearity, and that we can stack over several layers. And this we will do again with our, or will be like parts of the CNNs and RNNs. However, the important thing is that we want to address how can we like deal with non-fixed number inputs. Why is this important? For example, for sequence, there are a lot of sequences out there where we have to deal with sequential data. When I'll take examples, it will be mainly based on text and audio. That are two typical examples where we use a lot of like network architectures to protest them, to process them, and they are typically like in a sequence. And but however, there's a lot of other data out there. I mean, there can be videos where you have even like 3D thing you can view it. There's a lot of sensor data. Like if you have now all your sensor information, you have your health trackers, you want to like learn something from them, then this is all like sequential data where you need to predict. Or think of like you want to make money. So if you think of stock market or so if you try to observe the stock market, predict something, this is also typically sequential data, and you have to somehow deal with this. If we think of that in the neural network representation, what we have there is, on the one hand, we have the input lengths, and then we assume here always that we have discretized sequences. So at each position, we have then a hidden representation, a vector again, and that is then again a fixed size vector. So we always assume that at each position, there we have a fixed size representation. There can be for words. We have seen that you can map them with a one-hot encoding. We have done that for categorical data. Words are also categorical data. We looked into the one-hot representation and how you can then map them. So there is a lot of things that you can have in a sequence. However, our assumption is here first that is in discretized time steps, and at each time step we still have a fixed size representation. However, in most of this data, this can be handled somewhere in this way. And of course, you might go to even more data. So you can do a lot of these things also on multidimensional data. We'll touch upon this a bit. So of course, if you think about an image that's typically viewed as a 2D array, where like at each position you, for example, have 3 colors or so, and you can then have voxels for 3D information, something like that. Then you have even 3D data. So you can extend that easily to several dimensions. There's one thing which makes things a bit more challenging in 2D compared to 1D. Can somebody, if you think about your also the model types we looked into last time. We talked about that you store things in some global vector or something and then process it step by step. Yeah. Yes, exactly. So it's a bit like easier. If you have a sequence, there's like always a predecessor, that's all. And there is an order which you can easily put things. For a 2D, putting all 2D pixels in a linear order, of course, there's ways you can do it row-wise or column-wise, or you have to have more complex relations. Like you have the top border and the previous one. That's why we'll see that some type of networks is easily transferable to 2D things. For others, it's also possible, like for RNN, there is a 2D version of that, but things get just more complicated in how to calculate that. Yeah, so what is the challenge? On the one hand, I mean, just dealing with the data is a challenge. So we have variable length input. So a sentence can be I go home or my friend goes home, and both of them should work. If you think about an audio sample and you want to recognize it, it can be shorter or longer, even if it's exactly the same sequence. I can say I go home. Middle speed, can say I go home. Then this sequence will be a lot shorter. I can say I go home, and the sequence will be a lot longer. And even if it's the same label sequence, we need to like handle different types of inputs here. And our input vectors, I mean, we need to discretize that with something that's more audio processing, which we'll not cover in detail here. But if you want to do that, you have to, somehow in the end, you'll have different number of vectors to process it. Or if you think about images, it's also there. You can have the same image in different resolutions, like from 1 to 1 pixel to 2 pixel to 100 to 100 pixels. So here you have like somehow 10,000 input examples, while 5 times 5, you have 20 examples, your sequence length somehow. So you need to be somehow able to deal with all of that in a decent word. And the standard neural network, at least, doesn't that easily work with. I mean, now, I guess you could argue if you have only a standard neural network, which would be maybe your way of dealing with it. Is there an easy solution? You have variable size input. What can you do to still handle it? Just imagine you want to do this pixel like an image and you only have a standard feed-forward network. How could you put things in a neural network still with a fixed size? Yeah. That's already we'll cover. I mean, that's a bit in the direction of time-delayed neural network CNN, so it's right. We will cover that, but then you have to apply the network several times. I mean, the easiest solution is you can somehow assume that's the largest input size and then fill up the rest with ones. Or downscale it a bit. I mean, for image, you can downscale. For words, it's a bit harder. You cannot like easily compress, but you can assume like your longest sentence is 100 words. I mean, it might not be always right. And there you will have sometimes a problem, but you'll solve a lot of tasks. And then you just like fiddle the last one with it. However, this is still not really good, because another problem which is related to that is that it should be somehow at least shift invariant. So home has the same meaning in I go home and my friend goes home. If you put a feed-forward neural network on this sentence and just pad it, you once have to learn that home on the third position has a meaning, and once you have to learn that word on the fourth position has a meaning. If you remember, the easiest thing to deal with it, we would concatenate all the representation of the word, and then the features for home would be completely different as the features for home at the fourth position. So you once have to learn that home means something at the third position and independently learn that home needs to mean something at the fourth position. And this is, of course, very, very inefficient. I mean, a lot of words occur only very few times, and then you might at some point know that what home means in the first, second, and third position. But if you then think about the 57th position, you might never seen that. But you as a human, you're able to understand what home means, even if it's like somewhere in the sentence. The same is for audio. I mean, you can recognize what an A is. And it doesn't really matter if the A is at the beginning of the word, at the end of the word, in the middle of the sentence. So some of these features are there always. And therefore, you should be able to recognize some things like shift invariant. Of course, you have to consider the context. And the word home might mean a bit of a different thing based at the beginning or the end of the sentence. However, the basic concept you should first recognize and then maybe fuse it with your context. If you have to learn everything for each position, that's not really efficient. Another example is here. If you think about this image in images, you can recognize a cat here, 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 and so on. If you would think of that now, you put just the whole image into a feed-forward neural network, you would have to learn what a cat here is, and what a cat here is, and what a cat here is. And the input representation is completely different. So it wouldn't be easy to really learn that this is a cat. So somehow just putting like the whole image into a feed-forward neural network is not really efficient because we want to learn information independent of where they are in the image, independent of where they are on the word, and so on. Yes? Yeah, but therefore you need to have the ability of filters which go over the image and detect something. And we'll, in the basic feed forward, you don't have that. We'll see. If we now have a CNN or TDNN, what we cover today, that is exactly the idea, that you can do that. So that's very nice, this example of a filter. And that was even there before neural networks. So there is the idea, I mean, there were these ideas of how can you identify something in an image. And one important information, of course, is to somehow detect edges, like where there are edges of an object that can help you to detect. So, and you can do that without any type of deep learning. There's a very easy filter to do that. For each pixel, you calculate the new value is the current value minus the value from the neighboring word. And if you apply that, you see what happens there. And it's a bit hard to detect, but you see now the values are exactly there different where there is a big difference. So you nicely see how there's like an edge detection happening. So you like the idea of going with some filter over the whole image or like over your whole input and detect something is somehow very interesting because you can identify somehow local structure which can help you to identify things and which can then also help you to identify them shift invariant, so anywhere on the image. So it's no longer important whether it's on the top or at the bottom or so. You can just go over it and identify it. And this, yeah, it is somehow important. So the question is, how can we do that with some type of neural network? So the motivation for our new first type of architecture we want to do is we want to detect patterns independent of time or position within your input and without any type of pre-segmentation. So we just want to detect it anywhere on your image. And for this, there is a typical architecture. There's like two namings of that. There minor difference, but mainly the idea is always the same thing. It's like either referred to as time delayed neural network, which was presented for doing this exactly on speech first. So you go over your speech signal and try to identify, oh, this is a and this is a B and so on. And the same thing you can do, of course, in images, and there it's typically called a convolutional neural network. So what is the basic idea? I mean, we said there is this idea of that you have a filter which runs over your sequence and detects something. And exactly the same thing you can now do with a neural network. So imagine you have your input sequence 1, 2, 3, 4, 5. And now we just apply our same neural network several times on the input image. So we start maybe with at the beginning at the position 1, 2, 3. So we take the 1, 2, 3 as input and then apply a normal neural network. So we put 1, 2, 3 in there, and then you can apply feed-forward neural network, or at least one layer, so a linear transformation, and then an activation function, and then you have a new hidden representation. The size is fixed. You can define how big the size is. So you get as input somehow 3 vectors, and you apply them and get a new vector. And with this one, you somehow go over your sequence and apply them all the time. The same way as we did before with the edge detection. So we go over our image or our sequence and always apply exactly the same function on that. How does that go mathematically? So what we have is somehow we have, let's say, 3 inputs, and all of them are like n-dimensional vectors. And then we need a linear layer, which is not n cross m. Does anybody see the error? What would be the right dimension of our matrix here? We're putting a linear projection, onto this, a linear projection. What should be the size? So input size is 3 times n. We have here 1n, 1n, and 1n input. So the W should be 3n times m there. And then we put in output activation. So overall, to calculate our hidden representation, which has size m, is we apply our matrix multiplication on the concatenation of our 3 inputs and then do our activation. This looks exactly as a MLP as before. The difference is that we are not applying our MLP once, like our projection once on our input, but we are applying it several times. So to make it graphically, so we could, for example, start here. So the first thing is we apply it to 1, 2, 3. So always like some of the previous n and the next m tokens and so on. So here we can, directly apply it. And then we can apply it just another time. And there we get our next hidden state. So now we use as input x2, x3, x4, and get again our new output. So we have now 2 output vectors there, in which are both m-dimensional. And we can do it another time. So we do it until we are at the end of the thing. So what we're doing is this type of linear projection, and then the activation function we apply always on our input. And this is often referred to as the kernel of the CNN. When you now think of the kernel, there is some hyperparameters, of course. So this is the general idea. You can apply the same network at each position, and then you can detect shift invariance. So it doesn't really matter where your word home now stands. At some point, your word home will be in the middle, and you'll generate a representation for that. So if you have this, or if you have a in my home and you have a kernel with 3, then at some point in the sentence, in my home will be exactly as the input, and you'll get a hidden representation for this phrase in my home. So you can detect that in my home was in there. And it doesn't really matter where it is, because you just shift over everything. But you see there already one question, and one hyperparameter is like, what is your size of the kernel? You can apply a kernel of size 3 as we had. So that would be then the function which is always applied to xi plus 1, and xi plus 2. I mean, how you define that now, if you're going back and forth or only forth in the future is more definition. So this would be like a kernel size of 3 on top. Another thing you could do is like a kernel size of 5, for example. If you think, oh, more context is important to understand that, then it might be better to use a larger kernel size. So if you need more and more context to understand your current thing, then it makes sense to have a larger kernel size. Then anybody have, I mean, this now is only a reason to increase. So is there also a reason to maybe have not too big kernel size, but smaller ones? Any suggestion? Yes? Faster, yes. That's a good point, but it's not only about computation. I think it's very related to it. Even if you would have unlimited computation, there might be another reason for having smaller kernel sizes. Yeah. Yeah, I mean, the second one is completely right. Now, first, how we stack will come shortly too. But I mean, even without stacking, the reason for having smaller ones is to have less parameters. Here you have your metrics, we said is 3n times m, while here it would be 5m times n. So you have like more and more parameters, your bigger your field is, and then might be then difficult to work with and more difficult to learn. It's not only about, I mean, it's about computation, but the other is also about learning. The more parameters you have, the more data you will need. At some point, you might not have enough data to learn your things, so you need in there be more efficient. Of course, it might also be that you want to model some things which are like more local and more global. And then the idea is, as you always do in neural networks, just combine things. And that's, of course, easy. You can also have kernels with, have different kernels. So what you can, for example, do is you can have multiple kernels and then just concatenate your hidden representations. So you can, for example, have one 2-dimensional and one 5-dimensional kernel. You combine them both, and then it is possible. Yes? No, that would be in the same layer. So you can have that is why we are putting them, like we're concatenating them. So they would calculate it in parallel. So very good question. So we would calculate these two kernels in parallel and then just put the two hidden representations together. So we could have one kernel, one part which looks more on the wider context, and the other one which looks more on the shorter context. But it's a very good point. You can, of course, stack things now, and then you can increase your receptive field. So your H can now easily be again input to the next convolutional, which will be maybe again 3. So you would put H1, H2, and H3 into a new, which gets you K1 or so. And then you see that, of course, there is an overlap, but H1 gets as first input X1, while H3 goes up to X5 at the end. So you would have as an input from X1 to X5 all the way up into one hidden representation. So by stacking them up, you can increase also your receptive field, as mentioned already at the beginning. So can you also have variable size kernels? I mean, that would be the other idea. If it's sometimes good to have 3 and sometimes good to have 5, maybe it's also good to have some which can do a bit like both. Yes? You shouldn't do it. That's a good point. But could you easily do it? Or is there some, yeah? You understand the concept, that is true. So you could do some hacks around it, but keep in mind that directly it doesn't work, because we again have this restriction that we have a linear transformation afterwards, which needs a fixed size input. You can have this workaround where you sometimes fill and sometimes mask or set them to 0. But in generally, your function here always has to assume the same number of parameters in there. So it's at least not directly possible to have a variable size kernel. I agree there is some workarounds on that, but as a direct solution, and it's important to remember that, yeah, we can handle variable size, but only by applying the same function several times, and each application of the function, again, needs somehow a fixed size input in there. Yeah, and one important question is then, how many elements do we have in the end? So if we are doing that, how many output elements we have? So if we assume that we have n input elements, you see nicely here, if you have in the end n minus k output elements. So if we have 5 input elements and our k plus 1, and our kernel size is 3, then you have 5 n minus k plus 1. So then you have 3 output elements there, while if you have 5 elements, we have 1 out there. So you see, you're always reducing because you have somehow here the overlap, because it always takes more inputs than outputs. So we'll look at a way around that. But first, if you just apply the normal convolution at each position, you will a bit reduce your number of elements by a constant factor, so by k or k minus 1. There's another way of maybe reducing them more, and especially if you have long kernels, you have here a lot of overlap. Therefore, there is the other parameter, which is a stride. So now we always get one step further. That's what we always did here. However, if you have a long overlap, it might make more efficient and make more sense to not always just shift by one position, but shift by several positions. So for example, here it's we see also the shift by 2. So where we are not putting in here 1, we are shifting not by 1, but we are shifting by 2. So if you say your receptor field is quite big, there's maybe not a big difference by just going 1 pixel by a pixel or so. So you have then it might make sense to just go more, and that is the shift. So if you have a shift of 2, that means that position I, you're not at I plus 1 and I plus 2, but you're at 2i minus 1, 2i, and 2i plus 1. So you're shifting just by more positions by this. And then there is the final thing, that you might want to not reduce your number of elements by this constant factor k. And that can be easily addressed by having some type of padding in there. So you can pad at the beginning, maybe you can pad at the end. It's a bit like how you want to have the correspondence into it. So in the end, of course, your sequence looks a bit different. But if you're the nice thing, for example, if you have this way, then somehow you see that the upper one always corresponds to this word and the corresponding one. So if you want to interpret this as somehow a hidden representation of this word, then it makes more sense to take the left and right neighbor than taking the next 2 words, because it's somehow always focusing on this word. But by, for example, putting then 1 in the front and 1 at the end, you have now exactly the same sequence lengths. And you can use them to process further, especially if you want to have this one-to-one mapping. If you want to, we last time had this example that you want to classify each element in a sequence or do something for each element in a sequence, then of course it's important to not reduce your number of elements. By using padding, you can do that, and there's different ways of how you can do the padding. I mean, you can pad with zeros. You can also pad with something learned. Mostly that's not super important, because you're learning your weight matrix, so you can somehow learn something reasonable to get out of that. But that is mainly then that for the further processing, it's of course easier if you not have to think about, or if you especially merge different kernels, this ensures that your size of the different kernels is the same. Otherwise, this type of merging, of course, gets complicated if you then have different sequence lengths for the kernels with 1 and kernels with 5 and 3 or something. Before we are going now to the 2D case, any more questions about that? So here the extension to two-dimensional field is not really difficult. The only thing we are doing differently is that we are like now specifying our kernel size not as a 1D parameter, but as a two-dimensional. So for example, we could have a kernel which has size 3, 2. So 3 in the one dimension and 2 in the one in the other, and then we can shift again over our input matrix and apply. So you could like now take these 6 input elements and calculate a new hidden state, and then you would shift 1 to the right and do the same operation there and get a new hidden state. And then you can shift over all possible positions in your element, in your input, and get new hidden states, and which are always like considering then the neighborhood, and the neighborhood is this time two-dimensional. So you are both like considering your neighbors in the x dimensions as well as in the y dimension. In this type of neural networks, there is, typically or often there is in between then some type of pooling, or at least at the end, that you either pool over everything or over somehow a part of it, and which you then do like the max. So the max pooling is a default thing. If you want to now go from the variable size input into a fixed size representation, we've seen that, then you can do very simple pooling, and that is like at least typically combined with convolutional neural networks, that you're trying to do this max pooling. The idea is you have the filters which detect something, so they detect whether there is something or not. And with a max pooling, you can then do, in the whole area which I go over, did it occur or not, by taking the maximum of that. So this is like how it's like more conceptual done. The question is how is it like best to be implemented? And for the implementation, it's maybe better to see it again as one like feed-forward neural network, which always looks different for different inputs. So yeah, sorry. I mean, there's a lot of definitions of kernels, but in this way, it's like typically meant as a filter, yes. So from an implementation point of view, what you typically have to think about this is as an unrolled network. So the idea is you have now your convolution which goes over your input. You can now map that into a more looking standard feed-forward neural network by building a dedicated one for each input that we have. So if you have now an input which has a length 5, you can add, for example, your padding, and now you can apply your convolution there at each position. So you see we have here a kernel of size 3, which has the x1, x2, and x3 input. So yellow is connecting to x1, or to the first input, blue to the second, and purple to the third. And then you're like applying that at each position, but you can do that somehow into one big neural network. So now this is just one feed-forward neural network in the end, where you apply different connections here to the next one. You see that they are like the way of doing that now, of handling variable input, is that you duplicate your weights at different positions. You see that the connection between 0 and the first one, and the first one and the second, and the second and the third hidden state, they are all yellow, meaning they are all the same. And thereby you can extend your network to any variable size by copying it so many times as you need it. And the nice thing is, if you do that, now we know how to train it. So this one we can train as we are always doing it, because that is now exactly the same computational graph as we had for the feed-forward neural network. The only difference is that we are not having one architecture which is fixed for all inputs, but we are always building one dedicated for your input. So it's like a bit like how you view it. So the previous view was we have a fixed neural network and we let it go over our input. And so, yeah. While here we're viewing it, we have one input, then we build a dedicated neural network for it by copying things, and then we can train it or apply it and so on. And how you train it then is quite straightforward. I mean, we know how to do the feed forward, the forward pass. So we can do a forward pass, we can calculate our loss, and then we can do our backward pass and do that exactly the same thing as we are doing to feed for normal neural networks. However, there's one challenge which we should keep in mind. Any idea which could be a bit more complicated, or what we have to keep in mind when training that? What is the next step after you've done your backward pass? Yes, and the update weights, do we have to consider there something? I think it's exactly the right direction. It's even easier than you thought. What you have to do when updating, you have to remember that you share your weights. So you have to somehow keep the weights the same. So if you would now just update the weights independently, this yellow weight here might or will probably get a different gradient than this one. And so if you change the weight, this one in the next step will be different than this one. And of course that we don't want to have, because we have to we have to apply the same operation all the time. So we have to ensure that our original weights keep in sync and they are not changing. So if you copy, I mean, we said we duplicated our weights. So if we duplicated them, we have to now be careful that if we change them, we are changing all duplications and not only like the one instantiation of that. However, this is quite straightforward, because what we can do is just we can average all our gradients that we have and then update the joint one with the average. So here it's seen it's looking a bit worse than it really is. So if you want to, for example, update our yellow one, this update is based on the gradient that we get from the backpropagation from 0 to 1, the one from 1 to 2, the one from 2 to 3, from 3 to 4, and from 4 to 5. And for the blue one, it's based on the weights from 1 to 1, from 2 to 2, 2 to 3 to 3, and so on. So that just means when you update, you're not updating like now the original implementation, but you're updating each individual, like you're first accumulating your weights for the different instantiations and then updating them all together. I mean, you anyway do that normally because you're not doing one update for each example, but you average over all examples. Now you just do another averaging. So you're not only averaging over all examples, but also over all occurrences within one example. What? No, occurrences. Okay, sorry, good point. So like, I mean, if you have, normally you're not updating like for each example individual, but you have maybe 5 examples. So there you have the same weight already 5 times, and you're always doing the average over all examples. And now you're also doing the average over all times it occurs in the single example you have here. And yeah, with this, you can then stack things in larger layers as you see here. So that is, we already yes, spoke about that. So this is, for example, the LeanNet for graphics, where you do different convolutions. Then you maybe do subsampling, where you make the thing smaller. You do like the max pooling in there. then you have different like convolutional layers there with different maps. In the end, you maybe have an overall global max pooling. Then you might have several feed-forward layers, and that's then your output layer. So you can stack now, of course, these different convolution layers over and over again to have a bigger receptive field and then get more global context. So you first maybe have more local context. That is nice. So you first detect more like local features, small like in image, like maybe small edges and so on. And the higher you get, you have a bigger field, and then you can detect bigger captures, like is it a face or things like that. So in total, you can then the nice thing is of TDNNs and CNNs is that they can handle variable size inputs, and they can handle local context, and therefore are shift invariant. However, there is one there is also a disadvantage. You always can only detect things within your receptive fields. So like more a global view on that is difficult. You don't see like everything. There is a workaround on that by stacking many layers and having a very large receptive field. However, there is not really things that you like easily can detect more global information. Yeah, before we are going to the other type of network, afterwards, any questions to this? Yes? So, I mean, there is work on specific design more in the vision context, which try to better handle this. The hope is if you have a small receptive field, it might recognize it first independently, and you have an abstraction so you can deal with it. But I think there is dedicated, more advanced, focused on vision things which try to explicitly handle that. The other way, of course, you can handle that is by data augmentation, by like putting different rotations into your image so that the model like is aware of different rotations and can handle that. Yes? No, it's like the size of like how many input neurons or inputs like influence one hidden state. So if in one layer the receptive field is 3, if you have a kernel size of 3, but if you stack them now, like if you stack 2, 3 on top of each other, it should be 5. So you get like the more you stack, the bigger your receptive field is. I mean, it depends also on how you shift. So it really depends on your architecture. How much do you shift? If you shift, then of course it's increasing more. So there's not a straightforward calculation. I mean, there is a calculation, but it really depends on it. I mean, if you think about this with a shift here, if you have a shift of 3, then you have here already with afterwards a kernel size of 2, you have a receptive field of 5 because they have less overlap, the lower 2 one. These two together, which you could put in a new layer on top, which together would mark all of these 5. While up there, if you shift only by one position, it will be less. Yeah, but I mean, for one kernel, then it's easy. Then it's a kernel size. But the interesting thing is like how many are if you stack them, because then they can be like a lot bigger field. Any more questions? Good. Yeah, with this we can then look into a different way of handling context and a shift invariant. And that is the idea. Maybe it's also good to store somehow the global context. So not like treat each one and go over it and treat it independently, but somehow have a standard, another hidden representation, which stores all the things that we have done until now. And then you can receive, like, iterate through your data and always get more. And this, of course, like, assumes there is some type of order in your data. So the idea is you start at position 1, you like generate a new hidden representation, green here, based on your current input and the previous hidden representation. Position 1, that is, of course, a bit difficult. There is no previous one, so you have to somehow initialize here the very left green one with something. And then you go to the next one. And this one, you apply again your new input, your previous hidden representation, and calculate a new hidden representation. And so you can go over, and now the nice thing is, when we'll analyze this, your last hidden representation, your receptor field, is a full input. So this is influenced by everything. So you see that to get this one, you have the previous hidden state, which is influenced by 3. To get this hidden state, you have the influence from the previous input, which was 2, and that was also influenced by 1. So you somehow have information of your whole sequence in the last hidden state, which is, the main, or like one important idea of RNNs, that you somehow store information in there. Think it of a storing of the history, and you like go step by step and look which additional information you have, add them, and then you have, in the final thing, you have all your information in there. Historically, there were like 2 big ideas of that. And the one thing is what people refer to as the Elman networks, so that you somehow take your hidden representation, you have it from the last state, as I did before, copy it and use it as the input to the new one. So here you're doing a bit of a different trick. You'll see already, we'll come to that. You again have somehow a fixed size representation, but we are doing that by taking the last hidden state also as a new input. So you somehow take the output of your layer as the input to the new layer. And there's also, you see the recurrent name in there. So if you draw that as a graph here, you see the recurrence. So to calculate your new hidden state, it's not only based on your input, but it's also based on your previous hidden state. So we have this recurrent, the recurrent arc in our like drawing of how the network looks like. The other idea was to use the output and use it as an input. It's called Jordan networks. However, this is not what is nowadays typically used. So all the architecture more looks like what we have as Elman networks, so that our current hidden state is always used also as an input. And you nicely see again, we have mainly, again, some type of feed-forward neural network in there. So we again have a linear projection. So where we have the difference is this time, it's not that we put in several inputs. We only take one input, so the current xt, but we have another input to it, which is our previous hidden state. So we are somehow copying our previous hidden state here. And now our function, which we're using, is based on our hidden representation and the previous xt. So you see it's very, very similar. So you take your previous hidden state and your xt, you concatenate them, you apply maybe a linear projection to it, an activation function, and that is. So then you would have a vanilla RNN to it. So it's again, somehow you apply the same network at each position. The only difference is what your input is. The input is not the other inputs, but the input is the previous hidden state. Or shown here in the graph together. So the difference is really that we are now having somehow connections within a layer. And we'll see that is, of course, sometimes a bit more difficult for calculation. So before we had that we applied the same network at each position, but the inputs came only from the previous layer. And now we see that the input comes on the one end from the previous layer, but also from the same layer as the previous hidden state in there. Yes? Yeah, so that is similar to your padding. So you have to, so here that is what you really have here is the first green state there. You have to somehow initialize that. You can either learn that as parameters. You can just initialize it as zeros or as ones. Typically, since you are learning the mapping from there to your first hidden state, it's not super important how you initialize them at the beginning. I mean, they should be fixed. So you should have some good reason to do that, but you can either do like with some fixed values, or you can learn them in a way that they are initialized. And this is like the vanilla, the default RNN that we'll have. There is, I mean, if we're talking now about different RNNs, the only difference is mainly how you define your transfer function. So your function depends on the one end on your current hidden state and on your current input, and predicts then the next hidden state. And this can then manifest how you're doing that. There is like, for example, I mean, we'll first look at the simple recurrent neural network, which does that really as simple as possible. Then there is other things like gated recurrent units where you can do things like that, or we'll look then more into detail into long short-term memories. But in all of them, the idea is that you are, have to somehow do this type of function. And then we're doing the same unrolling. So you can see these two views of unrolled or this representation similarly as we had with the CNN. So you go over with your feed-forward neural network at each position and calculate that. The only difference is your input is now not from the lower layers, but from the same layer. And you can unroll it to have, again, the look as if it's a full layer. So yeah, how do we calculate it? So the easiest version is the same as we have before. We take an activation function. We then take the one way multiplying is with your previous hidden state. That's WH, for example. Then you have WX, which takes a transformation of your input. We combine them both. We add them up. For example, we have a bias, and that's our final result that we'll have. And yeah, this allows us to then generate any type of or then again, like process any length of input. And yeah, then you mainly combine your memory that you have. So think about this H as your memory with your new input, and you combine it at each position. And then you can see, oh, based on what I've learned before and what I got as new input, this is my new things that I should know. What you now can do is similar to what we have done with the CNN. We can unroll it in order to get a normal feed-forward neural network. Of course, the architecture now looks a bit different, and we again have to do this sharing of weights so that we share the weights for the same thing. So if we unroll it for two positions, for example, we have our H0 as one input, I1, I2, and then the weights between H0 and H1 is the same as the weights between H1 and H2, and the weights between I1 and H1 is the same as the ones between I2 and H2. You always apply the same operation at each position, and you can unroll it for variable lengths outputs here. Of course, now viewing that as a feed-forward network, you have to you have to tilt it a bit because you have to calculate from the left to the right now. So you cannot just go upward because H2 is depending on H1. So if you view it as a hidden as a feed forward neural network, H1 and H2 cannot be in the same layer, because we said that we always calculate only for the next layer. So somehow your input layer would be H0, I1, I2, I3, I4, and then you would have H1 as your first hidden layer, H2 as your second hidden layer, H3 as a third, and H4 as a fourth. So they would somehow be stacked up, and you would always have connection, like skip connection directly to the bottom. Which also, again, shows you a bit one thing which might be here more complicated. If you think about GPU calculation and things like that. Yes? Yes, exactly. So we can't like calculate the full layer in parallel as we did for the CNN, because the first layer was only depending on the input, but here they depend on each. So if you have a sequence, you have to calculate things from left to right, and you cannot process them somehow in parallel. Yeah, look at a more like one toy example at the beginning. Just imagine you want to have an RNN which just sums up your inputs. So you're putting in numbers, and your output should always be the current sum of everything. And because of math, it's easier. So we're just taking weights here and no activation function in between. So what we're doing is your new hidden state is WH times our previous hidden state plus WI times the input. And for the output is W0 times H. And so H and I are just like scalars now. So W also, to make things easier. Does anybody have already an idea what our W's should look like? If the output should just always be the sum of all the elements we had until now. I agree. It's maybe a bit complicated for just getting it out of the hand. Then I think it's very, very easy. But yes. That's already too. I mean, W is just just a scalar here, because we are just putting in one scalar at a time. So one number and just summing up. So you don't need a complicated eigenmatrix or something like that. It's very easy. It's just like ones, then it works. So if all your weights are just one, then this is exactly happening. So we said our first hidden state. Oh, maybe one important thing is, of course, not one. What did I not put here? So in this case, one thing is important. It's not really shown here, so, but it's important. Otherwise, it won't work. Yeah. Yes. So you have to initialize your hidden state with 0, and then the first hidden state would be 1 times 3 plus 0 times 1, and you would here have a hidden state 3, and you would output 3, which is correct because that is your sum. Now in your next step, you put a 1, and now you see nicely that your hidden state is always 1 times your previous hidden state, so what you have stored, so the sum, plus 1 times your input, and that's just a sum, so it's 5, and that one you're outputting. So by going over it, you're just always summing up things, and in the end, you always will have the sum of everything. Yes? Yeah, I mean, you store somehow at each position the full history up to that. That's the whole idea of the memory. And that you can only do because you do the recursion. So you always have stored, I mean, here the history is the sum of everything, but you see that the output on the last is influenced by all others because it's the sum of that. If you change this element, also the last one is changed. No, you cannot compute in parallel easily because you have to, especially if you have the activation function, it's nonlinear again. So really to calculate the second hidden state, you need to know the first hidden state. And that's why, at least in this type, we'll later look at bit different networks where it's again possible, but a big disadvantage of RNNs in generally is that you have to process things sequentially. So you can only calculate your second hidden state when you know your first hidden state, because it depends on that. It can be, you can, for example, do like parallel process several examples. So there, and you can do smart things with different layers that you calculate different layers in parallel. So there is smart ways, but it's not dedicated designed for GPUs. That's right. And that's why, yeah, while they were very, very famous for a long time, RNN, they had a bit of a disadvantage when going for GPUs. Good. Yes. No, not. RNNs are still faster on GPUs than on CPUs, for example. So you can do things, and as I say, one easy thing is just process all your examples in parallel. At least in training, you can just do like 100 examples in parallel, then you still have a good parallelization. You can do, in some, I think Google did that once, that they you can already, if you now stack layers, if you have calculated the first one, you can then do the second one in the first layer, but also start with the first one in the second layer already. So you can more diagonally calculate things and speed things up. They are just not that well suited as CNNs, or what we'll see on Thursday, like transformer-based models to do that. Good. So any questions before we are looking into how to train things? So from the training perspective, it's similar. We now have, again, a sequence of inputs. We have a sequence of ground truths. The sequence lengths should have to be the same. So we have the one-to-one mapping layer. And then our neural networks generates outputs, which has also the same things. And we want to similarly measure or minimize the difference between the desired outputs and the outputs that we generated. So we'll have a loss function comparing L and Y, O and Y. And of course, we have to somehow think about that like O4 is not only influenced by X4, but also by X1. So we have to calculate that. And that we can do by unrolling it and then doing the whole back propagation again on the unrolled net. Because RNNs typically think of these steps as time steps. It's called back propagation through time. But again, the idea is the same thing. You're sharing the weights. So the weights between X1 and H1 is the same as the weights between X2 and H2 and so on. And that's why you have to jointly update them. So if you hear about a backpropagation to time, it's again the same idea as we had before. So we share the weights and we have to constrain them to be the same all the time. So we compute the gradients with a forward pass and the backward pass, and then we are later doing the averaging before we do the update. So if two weights are the same, so the weight J at time step T1 and T2, they should later be the same. You compute the two gradients, then you average the joint one by, or you update the one by the joint gradient. And also for that, we want to a bit have a look again at, because it's of course in some way a bit more complicated, because now gradients not only go from top to bottom, but they go from top to bottom and from left to right also. So let's think of this as a very small neural network. We have a recurrent neural network. We have like 3 inputs here, and we calculate. So the first thing we are doing is we're doing our forward pass. So we get inputs here at nodes 7, 8, and 9. We are putting them in, and then also to the right, and calculating our outputs 1, 2, and 3. This is our normal type of forward pass. Then we are doing the backward pass, and there we want to look now at a bit of different cases. So first, have a look at the very easy and straightforward case. That is the case here between 6 and 3. So when we calculate the backpropagation, we have one output, and that is calculated the way down. And yeah, so how we calculate the forward pass is the output at position T is W63, so the weight between 6 and 3 times our hidden representation at weight 6 is then the output at 3. If we are now doing the backpropagation, what we are interested is one, the derivation to weight 6 to the weight here down there to change the weight. Why do we need also the derivation to H6? Anybody remember why that's important? I mean, we are not want to change our hidden state. That's the loss. So we are calculating some type of loss and then taking the derivation of the loss towards the first output. That's on the backward path, the first step. But why are we interested in calculating the derivation with respect to our hidden state? 6? Yes? Yes, exactly. To backpropagate further, we need both. So the lower one here, the W3, we directly need to change the weight, and the A to H6 we need to backpropagate. As you see, we needed before already the one to the output. So to calculate the first one to the H6, it can be like, again, do the splitting and the backpropagation. So it's the derivation of the loss to the output times the derivation of the output to the hidden size 6. If we look at our function there, if we calculate the derivation there, that's exactly W63. And then if we are doing here this one with respect to W63, what we have to do is do the same thing, and now it's just H6 there. So we can easily calculate that, and this is calculated exactly the same way as we have done it for the feed-forward pass. Not for the normal MLP networks. So then there's like some a bit more complicated. I mean, one question is what to do like within the RNN. So we not only have to calculate the way down, but we also have to calculate this derivation between 5 and 6. So that's on the one hand, we want to again calculate the derivation with respect to weight 5 and 6, and once we want to calculate it with respect to H5, we can see how we calculate our hidden state there. So H6 is W56 times H5 plus W69 times I9. And what we're doing there is, again, we are taking our derivation here and then multiplying it either with H6 or with W56. So this is a nice thing. We can do it very simpler because on the second part, we can ignore if we do the derivation to either W56 or H5, this is always 0 and is not really of importance here. One thing I forgot to say, I did here some type of simplification. Do you see what type of simplification we did here to make the calculation of the derivation a bit simpler? Yes? Yes, so we simplified things here to make them a bit more clear. Normally, of course, you would have to also use a activation function, and then you also have to consider the activation function in there. However, that's exactly as we have done it in the initial lecture, so this should be the same, but the formulas get just quite complex, so we did this type of simplification here. So we see also in the case where we do like the backpropagation within one layer to the left, it's mainly the same type. Since we did the unrolling of the network, it's somehow very similar. There's one additional thing which we hadn't until now, and that is that we are getting losses at different positions. So before we had our top, we calculated our loss, and then we backpropagate the loss back. But now we're seeing we'll get a loss at node 2, at node 3, and at node 1. So we have to somehow consider all of them. And how that works, we will see here. When we calculate, for example, the derivation from 4 to 5, in order to calculate the derivation from 4 to 5, if you see that, it once gets a feedback signal from 2, so the loss 2, and it gets a feedback signal from loss 3. So at 2 different positions, we get this feedback signal. In order to get the overall loss is the sum of the individual losses. So the overall loss at 4 or 5 is a loss at 2 plus the loss at 3. To calculate the loss at 2, this is coming via 5 and then 2. And for the loss of 3, it's coming via 5 and then 6. So you just sum up the 2 losses again and multiply them exactly the same as. So it's also similarly possible. The only thing we have to consider that, so there's 2 extensions we had here. The one is we have to calculate also the backpropagation within a layer. And on the other hand, we have to consider that we are not getting feedback only at one position, but we might get feedback from different positions, and we have to add up all this type of feedbacks. And then it's only the last step. So we have to update our weights. That's now again similar as we had in the CNN. So we had 3 different original weights. So the one between our input and the hidden, the one between the hidden states, and the one between hidden and that. So we have 3 initial weights, and you see that 2 of them are occurring 3 times. So we have them between our input and the hidden states 3 times, 3 times between the hidden states and our input, and 2 times between the hidden states. This is now because of the simplification that we didn't have initialization. Otherwise, you would have here that also there. And yeah, you average them again the same way, and then you have the backpropagation. So you may have now what people refer to as backpropagation through time. What you really have to do is like you unroll your network, then it's all a feed-forward neural network, and you do all the backpropagation. And importantly, you keep your weights the same. So the shared weights have to be the same at each position. Yes? So you have the weight VH here, this one, which is between the input and the hidden. And that's occurring 3 times between 4 and 7, 5 and 8, and 6 and 9, for example. That's also the same weight. That is the weight WHH. That's in the middle line here. So that is, of course, the same. I mean, because you don't know how long your sequence is, so that's important. You don't know how your sequence is, so the weight between 2 hidden states has to be the same at each position. You always have to do the same matrix multiplication there, because you don't know how often that is. Always, if you're not sure what can be shared or not, what is shared or not, you have to think, oh, I can unroll it 2 more times, and I'm not allowed to have any more weights. All the weights which I once defined have to there can be no new ones arising in there. To have one more example, think of it, you have an input length of length 8, and you have an input length of the output is y1 to y6, and then you have this type of neural network. And now the question is, you have the weight x1, h2. So, these are like each big X there is like both a tuple here. So you have one input, then one hidden layer, and one output layer. So this is at one time step, and you're applying it over and over again. So if you now, and your overall error is again just the sum over all errors. So how many updates do you have to perform on the weights between your input layer and your middle layer? So we can also unroll that, then it's maybe more clear. So if you now calculate all the errors, how many updates do you sum up between your input layer and your output layer? Any suggestions for that? Or at least a bit of an intuition of how to calculate that. So think about if you have now, for example, yeah, maybe a bit of a simplification. So if you're at one position, at the fourth position here, you're seeing that you update the error at the fourth position is updating this weight 4 times. So it's one of this shared, one of this shared, one of this shared, and one of this shared. So if you're thinking about the error at position 4 is leading to 4 updates on this one. Based on this intuition, do you have an idea of how many updates in total, if your sequence length is 8, are happening to this weight? Yes? Not 8 squared, but nearly just a sum from 1 to 8. So the first error, the first one is only influencing it once. So it's only the direct connection. For the second error, it's like doing the first initialization of the second. So for that one, you have 1 plus 2 makes 3. And so you go on till 8, that's 8 times. So you have the sum from 1 to 8, and that should be hopefully 36. So this is like just with one sequence, you're seeing that like with one sequence of length 8, you're doing a lot of updates on the same weight, which of course you should somehow consider when thinking about learning rate and so on, that there can be a lot of updates to each of your weights if you apply them like on long sequences. Any more questions to this? Yes. Oh no, yeah, that is right. So that's our like, yeah, that's the gradients first, which you use to update your weights. Yeah, maybe that wasn't clearly formulated. Yeah, very good point. So you only normally sum them up and then do them in one update. So yeah, to be precise is like how many gradients you calculate here. I mean, it's also a bit of a, of course, now it depends on how you calculate your gradients, because what I said before is here I somehow did 2 gradients in one step. So to be efficient, you don't calculate all of the gradients here individually, but you sum up the gradients already when going up and so on. But still in order to understand how much influence it is, like you have like 8 times an update for this one weight that you have. Yes. It's like the last one is 8 plus 7 is the previous one plus 6 and so on. So you have the sum of everything. Okay, then we want to finish today with a bit going into starting with one problem with the RNNs. So the one problem is, of course, the calculation that it might not be always easy, but there's also a modeling perspective, a big issue, at least with vanilla RNNs, and that is the modeling of long-range dependency. I mean, we said this is a nice thing of RNNs. So we said the first input influences your last output. We've seen that with 8, but now, of course, in reality, we might have a lot longer things. And of course, that is something we want to have, but very difficult to calculate, we'll see. So if you think about that RNN that is reading a text, of course, it would be nice if everything influenced. So if you think about, again, a review, that like in the beginning, you had very well put together, amazing, and so on. and it should influence your last hidden state. So if you're doing your prediction, whether this is positive or negative, on your last hidden state, all these words which occur there somehow should influence. So you should have a very long way of, like, a long chain of influence. However, and that is what we want to show now in what is referred to as gradient vanishing and exploding, this calculation is not really good. And in a vanilla RNN, therefore, you won't typically learn this long range dependency that you have. What is a problem? The problem is that you really need to propagate these things all the way back. And that gets somehow a bit problematic. So we did look into this calculation. So the loss with respect to H14 is WH, which is here the weight between the hidden state again. So if you have an activation function, it's the derivation of the activation function, and then the loss at position at the last one as 150. And if we are going to 113 with respect to H13, you see that you're like multiplying this now once more again. That's like the backpropagation. So you're always multiplying here the things, and you see you always have your weight in, then you have the derivation of the hidden state, but each time you have here in there the weight weight H in there. And for relative few number of steps, that is fine. However, things get complicated if you repeat that very, very often. So if you want to calculate your loss at the last position here with respect to a hidden state 50, then you would continue this. So then you would have the loss with respect to H15, then the loss of 15 with respect to H16, and so on. If you do the calculation, you always have there your weight matrix WH in there, and you would have it 65 times in there. So you have this loss 65 times in your product, calculating this thing in there. What does it mean? So just assuming this is not a matrix, but that is just a single a scalar value, what that means, if your weight is 1.1, you already have at position 15, 460 times your loss. If it's a bit lower, like 0.9, you have 0.001 times your loss. So you're seeing that this is very sensitive to the loss, and if it's a bit higher than 1, you're having exploding gradients. Your gradient gets very, very high. If you have values that are a bit below 0, a bit below 1, you have vanishing gradients, and your values get very, very small. And that, of course, isn't really good for training. I mean, you're updating based on these weights. So either you do nearly no updates because your gradients is very small and you're not really learning anything because you have very small gradients there, or you have very high gradients and then your numbers explode and you can't really learn anything. So so this is an essential problem. So of course you still can, I mean, if you have vanishing gradient, you might still learn direct interaction, because if you have later losses, but you only have a loss at the end, then the influence of the far away things, so the long range dependency, which we said is important and very nice and good, doesn't really work anymore because it doesn't have really any influence, or it leads to like an exploding gradient and you have very bad performance. So both of them are like somehow bad. So if you have exploding gradients, then your optimization algorithm doesn't work anymore. And if it's small gradients, then you're not really learning anything because it's not telling you to improve it. It's mainly staying all the way the same. So that seems not to be a very promising approach. So we have to somehow change a bit. I mean, you can do one thing like gradient clipping, so somehow keep the gradients fixed. So if the value of your gradient is too big, you limit it to some predefined value so that you're not jumping too far away, but you're somehow the maximum thing. But that, of course, is also only good for, for large gradients. If you don't have any gradient, you're not really going in a direction, and that's not very helpful. So this is a real challenge to standard vanilla RNN, and that's why we maybe have to address a bit the function that we're having. Yes? I mean, you can try, but it's all like a bit frickling. I mean, you can do the clipping is a bit doing that so that you're not going too far and so on. But yeah, you always have the problem that you might not really learn something. And therefore, what we will then look into mainly at the beginning on Thursday is the idea of what is referred to as long-term memory, long short-term memory things. So the idea is to build a neural network or like the unit in there which can address these problems by having somehow this WH, which is roughly 1 always, and also looking at input and output weight conflicts, so that you're not always writing into it, but you're learning when new informations are important, you filter them out and you put them in, and you have also an output gating mechanism to not always like output things, but learn when to output things and when they are maybe currently not important. So the idea is having a more complex activation function so that you somehow address a bit these problems. We will dive into the details next, so on Thursday, but before we finish, any more questions? Good, then thanks a lot for coming today, and we'll continue on that on Thursday.